If you have been using the Modeling Distributions series as a resource for your learning, I hope you have learned why we model distributions of data, the characteristics of these models, and some example models. In this short video, I want to review these concepts. There is no new instruction in this video. I believe it can be helpful to pause and summarize our learning. You can use this to help identify any lingering gaps in your understanding so that you can address these gaps before moving on to other topics. There are at least 3 purposes for using mathematical models as a description of a distribution of data. These models promote a basic understanding of the variables that we measure to obtain data. Understanding the density of data and how that changes as we move along the continuum of scores is a good step toward understanding how and why scores vary. Our goal in research is to understand how and why we observe particular outcomes, so we should first understand the distributions of these outcomes. A second purpose of a mathematical model is to provide a simple description of distributional form. For example, without showing you any data, I can state that the data obtained from a variable have a normal distribution, and you will have some understanding about the data obtained from that variable, won't you? Taking this understanding a step further, mathematical models facilitate the computation of percentile ranks and percentiles. Calculating percentile ranks and percentiles is a means of drilling deeper in our understanding of a distribution of data. Mathematical models are defined by a mathematical function. The data obtained from measuring a variable are the inputs to this function. The function output is the density of the modeled observations of those scores. In addition to mathematical operators and the input variable, our mathematical functions also include changeable values that we call parameters. Different parameters for the same function will define different models with the same distributional form. For example, for a normal distribution, changing the mean and standard deviation will yield a different normal distribution. We looked at 3 examples of mathematical models for distributions of data. The simplest of these is the uniform distribution. When variable outcomes have the same density along the entire range of scores, we have a uniform distribution of data. The second example is an exponential distribution. If data can be modeled with an exponential distribution, this means that the density of the distribution either consistently increases or consistently decreases as we move to higher and higher score values. The normal distribution is the most commonly used distribution in statistics. That is because if we measure naturally occurring data, we'll find that many of these data sets follow a normal distribution. Additionally, measures of our inventions, which we call constructs, are often purposefully developed to yield a normal distribution. Finally, and this goes without explanation at this point in your statistical life, the normal distribution will have important uses in statistical inference. If this review has sounded familiar and has had you nodding your head in agreement, then you should be ready for the next step in our adventure, exploring relationships among variables.